Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 16, and this problem asks us to label each compound as more or less reactive than benzene in your electrophilic aromatic substitution. So what we know about electron donating groups is that they make your benzene ring more reactive in electrophilic aromatic substitution, while electron withdrawing groups make your benzene less reactive in electrophilic aromatic substitution. The reason for that is because in EAS reactions, or electrophilic aromatic substitution reactions, your benzene acts as your nucleophile, and it's attacking some sort of electrophile. So here, there's actually no lone pair, but the two electrons in your pi bond will act as a nucleophile to attack your electrophile. Therefore, if you have more electron donating in your benzene group, that will make your nucleophile more electron rich and more reactive towards your electron poor electrophile. However, if you have electron withdrawing groups in your benzene, then you're actually taking away electron density from this pi bond, and you're making this less reactive to your electrophile. So what we know is that to determine the reactivity, or to determine the electron donating and electron withdrawing characteristics of your substituents on your benzene, you need to mostly consider the atom that's directly bounded to your benzene group. So we know that all R groups, or all alkyl groups, are electron donating. So carbon, these hydrogens, they all have electron density and electron cloud that can donate into your benzene, which can make your pi bond more nucleophilic, and therefore this will react faster. So it's more reactive than a standard benzene ring with no electron donating substituents on it. Let's see now in B. So in B, we have two alcohol groups. So yes, oxygen is more electronegative than carbon. So we are going to have some sort of inductive pull away from this benzene ring, inductive pull of electrons away from the benzene ring. However, we know, just like in a previous example, that the resonance form of making a fully negative charge in our benzene ring outweighs the inductive electron pull out of the benzene ring. So we know that because of resonance, because of the lone pairs on oxygen, we get a resonance structure that puts a full carb anion, a full negative charge in our benzene ring. And not only that, well, we have two oxygen atoms that can make two resonantly formed carb anions in our benzene ring. So now we have full negative charge in our benzene ring. Therefore, this is going to donate electron density into the benzene ring, making it more reactive than a typical benzene that has no alcohol group substituent. So this is more reactive. Now, what about this group? Well, in all the previous examples, we were only curious about the atom that's directly bounded to the benzene, but here we actually got to draw this out. So if I draw this out, it becomes clear that we actually have to investigate the entire functional group, not just the carbon atom. So if we draw this entire functional group, we see that we have some sort of ester group here. So now we actually have a resonance structure that can form, but this will actually put now a full positive charge in your benzene ring. So if you see this resonance structure that just formed, we actually now have the negative charge on this exocyclic oxygen atom, and now we have a carbocation in our benzene ring. So now we actually have an electron withdrawing group here because of this carbonyl group, and because of that, this is going to be less reactive than a typical benzene ring that wouldn't have this carbocation resonance structure being formed. And now we have this last example with nitrogen, but this nitrogen is not your typical nitrogen with a lone pair electron. It actually has a positively charged, it's a positively charged nitrogen, so it actually does not have any lone pairs, unlike this oxygen. So in the case of this oxygen, we knew that these lone pairs could donate into the ring to form a carbanion in your benzene ring, but this nitrogen here has no electrons to donate, no lone pairs to donate inside the ring. So the only thing that it can do is, because it's more electronegative than carbon, it can just inductively pull electrons out of your benzene ring, and therefore it will deactivate your benzene ring, making it less electron rich. So it's going to be less reactive than a typical benzene without this positively charged nitrogen atom on it.